Hey guys, welcome back to our next lesson. We are diving into a whole new unit here, and we're really gonna start to understand some of the big ideas of calculus. Our first section here is gonna focus on polynomials. So today's lesson is the continuity of polynomial functions. Our mindset message for today is that struggle grows your brain. Some of these deep concepts we're gonna dive into might challenge us a bit, but I just wanna remind you that struggle is important and your brain grows through that, but just keep pushing forward because you can do it and you can understand it. Our learning goals for today's lesson: first, to analyze polynomial functions. Next, to understand two theorems we're going to learn. The first one's called the change of sign theorem, and the next one is the intermediate value theorem. And then prior knowledge we need, more or less, would just be understanding what is a polynomial. So if you need to go back and do an internet search or something for that and remind yourself what that is. We've studied linear and quadratic polynomials in depth in the past, but we're going to be able to deal with some of the larger degree ones, and we're going to, I guess, talk about them in new ways. So let's dive into an informal definition first. Okay, so I'm going to call this informal vocab, and we'll give some examples, and then we'll dive into the more formal definition here. So a function is continuous on its domain if there are no breaks, holes, or jumps in its graph. That's a really intuitive way to understand it, is by just looking at its graph. Continuous kind of makes sense if you think about it. It just means it continues on, and it doesn't have any places where, if you were traveling, let's say you could think of the graph as like a road. If you were traveling on the road, you would never fall through a crack in the road or a hole or anywhere like that. Okay? And one fact about polynomials, so we're focusing on polynomials today, is that all polynomials are continuous everywhere. So their graphs just continue going on forever, and there's never going to be any breaks, holes, or jumps in them. So here are examples of some continuous functions we've learned about in the past. Y equals x squared, or any transformation of that is, well, we know it's a polynomial, and we already stated they're fully continuous. And you can just think this graph just goes forever outwards and up, and it has no issues as you travel along as far as breaks or anything, right? Another one we're familiar with would be y equals 2 to the power of x, or even other bases besides 2. They all have the same general shape, right? And again, they just continue on forever, and there's never any issues you get to if you're traveling along that curve. This one is not a polynomial, so I just want to point out an example of something we've seen before that is continuous, but it's not a polynomial. And then another polynomial, and we've seen this in our last lesson, we talked about some examples like these. So this one is fully in factored form, which means we know the x-intercepts, in this case -1 and +2. And because it's overall cubic, this one kind of has to go opposite directions on either end, right? This kind of up, down, up shape to it. And because we only know it crosses 3 times, it couldn't have crossed here at the 2 and then crossed again. It had to just touch right here at a vertex and then go back up. But either way, here's another example of one that is continuous. The graph just goes on, and it's like that forever. So here's a few non-continuous functions. One familiar one that we've seen in the not too distant past is y equals cosecant x, or even secant or tangent or cotangent. Any of those, they all have something in common, and they have vertical asymptotes. That causes a break in the graph. The graph itself is in pieces. All the pieces collectively are one single graph, but the graph itself is in separate pieces that never connect. So they would be not continuous, right? So these pieces just go up infinitely, and they never actually connect with each other. Another type of function that you may or may not be really familiar with, really this isn't anything you aren't familiar with, but it's maybe a new notation. We call these functions piecewise. Essentially, there's pieces of other individual functions that have been kind of spliced together into one function. So what we're saying is, when x is less than 2, so if I'm at 2 and when I'm below 2, the function behaves like x minus 3. Well, we know x minus 3, if we were to keep the whole thing, is just a line that goes forever like this, right? And its y-intercept is at negative 3. The problem is, if I did just let him go forever, and I want to also graph that at the same time, we also know x squared looks like this if I let it go forever. Well, if I wanted to consider these both together one whole function, kind of like the pieces of the cosecant, it's not a function because we know that there's multiple outputs for inputs, right? So what we had to do was kind of cut off the domain, and that's just like something we've talked about recently, right? Cutting the domain. And we've kind of spliced the pieces together as if they're just one function. So this does count as a function. The only thing about it is not continuous, because it might be continuous if we somehow made a function so that they met together here. But it has this jump in it, right? And we'll talk more about this one later, but that's kind of what's going on with this function. So we just finished talking about a very informal definition of what it means for a function to be continuous. And we've kind of looked big picture. We've looked at the whole graph and then scanned it to see if there's any specific locations where we have a problem, right? A break, a hole, a jump, whatever in the graph. So the actual definition of continuous, I guess we'll call it the more formal definition, focuses in on a specific point and gives us some language or a way to understand how we can define if it really is continuous there. So we're going from bigger and we're focusing a little bit more specifically here. I'm going to call this the semi-formal definition for continuous because you will learn a much more formal, the completely formal definition if and or when you take a calculus course. But for now, let's read this together. It's going to take a bit to understand, so it's really important that you maybe even pause and just read this through carefully and try to digest what it's saying, and then we'll break it down together. Okay? So a function f is continuous at an input a if you can make f of x as close as you want to f of a by making x close enough to a. Let me just very, very, very informally, again, help you understand what we're saying. Imagine we travel from both sides. Again, think about traveling along the curve as if it's a road. If I'm coming from either direction, what I'm saying is, can I get as close as I want to the actual output f of a? So I've drawn some arrows in here, and hopefully this should help just a little bit. So if you imagine, my x value, and it could be down there or above here. I kind of put either side there. If I get really close to the input, the actual input of A, is that going to make sure that, and you can imagine this x value has his own output, or if I placed another one up here, he has an output. But you can imagine if this x gets really close, this point travels along the curve closer and closer to the actual output, right? To the actual point we're considering on the curve. And you could also just consider the distance in the outputs. Is this actually getting closer and closer to there? Or we could start from the other side and let my x be here, and this point getting closer there. Okay? Essentially what we're saying is, if I continue to squeeze these two red points closer and closer together, can we guarantee that they're going to meet each other at the purple point? Okay? For now, that's as much as you really need to understand about this. Let's take a look at a non-example, because actually I think that's much more helpful to understand this definition with one that isn't continuous. Okay, so let's just call this example 1, or question 1. Why isn't the function f of x equals that? And this is one of the ones that we saw that was not continuous earlier. Why is it not continuous at the value x equals 2? One thing I forgot to mention before is sometimes people forget, why is this a closed circle and this one is open? If you think about how I've split the domain here, this piece right here, the squared one, I've included 2, and this one I've not included 2, right? So actually, everything up to 2, even 1.99999, right, is going to be part of this piece, but as soon as I get to 2, I jump up to this piece. But anyway, let's try to actually answer this question using the definition we just learned. So before we dive into the explanation with our new definition, just make sure it still makes sense to you why this is not continuous, okay? I forgot to mention earlier, there's another cool thing people talk about to help understand if it's continuous, is if you have the graph and you use your pen or pencil if you're drawing along the graph, can you draw with your pen or pencil along without ever having to lift it off your paper? In this one, we wouldn't. We'd have to lift it up and then start again up here, right? Well, let's actually use the definition we just learned to try to apply to this and see if we can figure this out. Here's an explanation I put together. We know that f of 2 equals 4. If you just look at this function, the second piece is the one I use when I'm actually equal to 2, right? And of course 2 is the input of interest here, because we can see that's where there's a break. If you were to go past 2 or before 2, the graphs actually look pretty nice. So maybe they are continuous in the rest of the pieces. But right here at x equals 2, we see that it's not continuous. So we know that the output here is 4, right? Watch what I said. But as x approaches 2 from the left, what I'm saying here is if I'm traveling towards x equals 2, so if I'm going this way from the left side, remember that the definition said I need to be able to get as close as I want to x, and that also gets us as close as I want to the actual output, right? But look what happens here. I can get as close as I want to 2 here from the left side, and I can get closer and closer. Remember, we're not actually getting to 2 yet, right? So let's say 1.99999 or something like that. Well, the problem is, as we get really close over here, we get close to an output of -1. But the actual output based on what the function says is 4. So because I'm not actually approaching the real output here, it means that there's a break. It's just kind of another way of saying that, right? So it says we get closer to -1, not 4. Now, if we were to come from this direction, we do actually approach the actual output based on what the function says. So there isn't really a problem with continuity if I'm looking at this piece, but there is a problem when I'm looking at this piece. Now you might think, okay, well, couldn't we just fix that by plugging in this hole? If I just fill this in right here? Well, again, we would still be approaching -1, or maybe bringing that down. If we were to actually have this piece and that piece where they really did meet each other, we would essentially make it be continuous. But as it is right here, it's not continuous. So why don't we apply kind of the same idea and ask the same question about the other non-continuous example we looked at, f of x equals cosecant x. But again, I apologize that I drew the wrong graph. I accidentally drew the graph of secant before. So this is the actual graph here of cosecant. And cosecant is undefined whenever sine is 0. So that's going to be here at 0, pi, 2 pi, etc. So multiples of pi. First thing to notice about this, actually, and this is probably the easiest way to answer this question, f of x isn't even defined at x equals pi. It's important that whatever input we're talking about actually works in the function in the first place, right? But we can still think about our reasoning that we just applied a moment ago with this one, but it'll be slightly different. The other way to think about it is, again, we're thinking about what happens as I get really close to the input we're asked about. How does the function behave? Well, if we approach pi from the left, we're in this piece. So if we're going towards pi, notice what happens. We're coming down here, and in this whole piece here, it's continuous, right? But as I get closer and closer to pi, the arrow here and the fact that there's an asymptote tells us that this just grows infinitely large positively, and we've already talked about how it never actually is allowed to use pi as an input in the first place. So it grows infinitely positive, infinitely large positive. And similarly, if I come from the right side, I'm now in this piece. This grows infinitely large as well, but negatively. Either way, it doesn't even approach a specific output in the first place, and so again, that helps us understand that it's not continuous. So again, just think about it. As I approach the input I'm asked from either side, how does the function behave? Are those 2 points going to meet together at one harmonious point, or is something bad going to happen?